Yep. All right. So we're back. We're going to talk about limits of rational functions as x goes to an infinity. Just quick review. You should know that a rational function is an irreducible polynomial divided by a polynomial. And it actually turns out that the end behavior model for those guys is kind of intuitive. So if the end behavior model for a polynomial was going to be the term of highest degree, well, it turns out the end behavior model for a rational function is just the term of highest degree divided by the term of highest degree. So it's the ratio of those two polynomials. So let's just get after it. So here we go. It says for each rational function, determine the end behavior model and then evaluate the limit. So we shouldn't even have to tell you the term determine the end behavior model. You're going to want to do that. So you're like, all right, so here's a limit problem. Again, the key, guys, is that you only use end behavior models if it's a limit to infinity. All right, so this is telling us, okay, use an EBM. So now what would it be? Well, it'd be, let's see, limit as x goes to infinity. I'm going to write an equivalent limit here. The end behavior model would be, well, the term of highest degree in the numerator is going to be that. So 2x cubed, right? Divided by the term of highest degree in the denominator, which I have to go ahead and take the coefficient. So that's going to be negative 5x cubed. Now with these problems, there'll be some simplifying you can do. You can see here that these x cubes, they're just going to cancel, right? And leave a little 1 behind, and you end up getting the limit of a constant, right? It's going to be the limit of 2 over negative 5, or negative 2/5. So maybe I'll just clean that up and write that this is what you'd get, right? So negative 2/5. So what is the limit of a constant? It's the constant itself, okay? So this guy right here, believe it or not, is the simplified EBM, and we actually got a number here, and this is good review. What does that mean? If you do a limit to infinity, you get a number, well, then that means you have a what? You have an HA, right? So this would mean that there's an HA at y equals negative 2/5. So chock full of good information here. Back in the day, in your pre-calc teacher, they may have taught you some silly like, hey, if the degrees are the same, right, then the coefficient is going to be your asymptote, and that's all fine and dandy and good stuff. But I just think it makes a lot more sense to approach it this way. That you're actually finding the end behavior by doing a limit to infinity, and it's pretty intuitive that it would make sense that it's the term that dominates in the top divided by the term that dominates in the bottom, right? For large values of x, those are the ones that carry the most weight. So then that quotient is going to be what you're going to approach. Okay. All right, let's take a look at this guy. Notice very similar problem. The only difference, I think, right, is just this exponent here. But watch how it changes the game a little bit. So again, it's a limit to infinity. So that is the key that says, hey, we should use an EBM. So what would it be? Well, let's see. I can rewrite this as the limit as x goes to infinity, term of highest degree in the numerator, right? The one that's going to dominate for large positive values of x is going to be 2x squared. One that's going to dominate in the denominator is going to be minus 5x cubed. Can I simplify this? I certainly can. Two factors of x here are going to go with two factors of x there. All right, so I'm going to get the limit as x goes to infinity of, hopefully you heard that, of 2 over negative 5x. And so now this goes back to what we learned the other day, where you have a constant being divided by something that is growing without bound, right? You keep dividing by a larger and larger number. So this whole limit is going to go to 0, all right? Which again, think about that. As x goes to the right forever, we're saying the functional value is approaching 0. Well, then that means, I know this wasn't part of the question, but heck, let's write it down. That means that there's a horizontal asymptote at y equals 0, otherwise known as the x-axis. Okay? All right, pretty good stuff. Let's keep rocking and rolling here. Let's do this so I can scroll down. I'm going to do this guy here. So again, you should maybe pause the video here and see what you come up with. All right, when you unpause it, now you come back, let's get after it. So here we go. It's a rational function. Again, how do I know it's a rational function? It's a degree 3 polynomial divided by a degree 1 polynomial, and I can't reduce it, right? So I probably should have stressed that in the first two, regardless. All right, so here we go. So limit as x goes to negative infinity, right, of, let's see here. Well, term of highest degree in the numerator, that's 2x cubed, right? Term of highest degree in the denominator, take the coefficient, it's going to be minus 5x. And then I'm going to spruce this, right? This factor of x goes with one of those factors of x. So if I rewrite this cleaned up, limit as x goes to negative infinity, I'm going to get negative 2/5, and then it looks like x squared. All right, so now this isn't constant over x. This is, all right, x squared. So the way I would do this is I would temporarily think of negative infinity. It's a really big negative number. Chuck it in for x and square it. What do you get? You get big and positive. Multiply it by negative 2/5. Now it's going to be big and negative. So you're going to get negative infinity here, which means that this wouldn't have an HA, because as I go to the left forever, as x goes to negative infinity, we're saying that this function is going down. All right. And those are limits of rational functions as x goes to infinity. Pretty simple to do. Next video, we'll do the guys down below. Be good.